Welcome. So I'm still McElory Hoffmann, and this is the Computer Science 144 video lectures. At this moment we discuss data structures and algorithms, and in particular we focus now on algorithms, important algorithms. The important ones that we've discussed so far was searching algorithms, and today the topic will be sorting algorithms. Remember, and I've said this multiple times before, and I'm going to say it multiple times hereafter as well, is that we have this way of analyzing the performance of algorithms, and what we want to do is we want to get smarter, better algorithms that would allow us to solve bigger problems that we cannot solve using normal techniques. Well, the brute force ways. So what we have is we have this performance measurement tools that would allow us to measure the performance of algorithms, and then based on that we can make comparisons on the running time of algorithms to decide which one is the best and which one we should use. So, for example, in the previous lecture that I've presented, when we've discussed sorting algorithms, not sorting algorithms, searching algorithms, I've shown that we can have a brute force method that runs in linear time, and then we have a better method that can run in log n times, and then we've come to the conclusion that if an algorithm is running in log n times, we would be able to solve problems that can not be solved on normal computer hardware. So we've always have this example that we've seen that we have this toaster, cell phone and Google supercomputer, and for the type of problem that I've specified, if you have a linear algorithm that would not run on a toaster, but if you have the logarithmic algorithm, that would indeed run on your toaster. So what we have now today is we're going to discuss sorting algorithms. So again, sorting algorithms are everywhere. We've seen them, perhaps you've not seen them so many times now that you know about them, or once you know about them you will see them definitely everywhere. So what is the sorting problem? So we are giving n items, and then we want to arrange them in some ascending order. So of course the order that you have to decide is arbitrary. You can decide what the order should be, but there should be some ascending order. And the applications are numerous. We cannot list them in this presentation. There are just too many of them, but some of them are listed over there. So in statistics, they are used there quite often. In databases, it's a common thing. I mean, if you can think of myself as a lecturer here at the university, usually when I get the class list for this class, I don't get the classes in some arbitrary order. I usually say, give me a class list, order them by name, and then the computer somewhere at IT or wherever they have the university's computers will sort the results and then give me the class list based on your surname, for example. But then as the marks come in, I'm usually interested in who has, for example, above 75 and who has below 75, or who has above 50 and who has below 50. And then I do another kind of sorting algorithm where I sort the same data based on another criterion. So here you can see also something else I'm mentioning. Based on the criterion, you can get different orderings of data depending on how I actually want the data to have. And then at some point you will get your marks from the system, and there you want to have an order in the subjects, maybe in alphabetical order of how you pass the courses. And for that is another sorting algorithm. So I mean, so we interact with sorting algorithms literally everywhere. There are some other places where they play a role. In data compression, computer graphics, they play a role. Scientific computing, you will see them. Really, they just everywhere. And there's an example of how we do sorting. So there I have a list of names: Hauser, Hong, Husu, Hayes, Haskell, Hanley, and Hornet. And then I have a list over there, and then they sorted in alphabetical order, so lexicographically sorted. So this is the kind of problems that we want to tackle. We want to do sorting. Now there are numerous sorting algorithms out there, and well, it's probably possible to discuss all of them, but I'm not going to discuss all of them in class. What we will do is we will again follow the same approach as we've done with the searching approach. In other words, in searching, what we've done is we've shown a brute force way and then do analysis on that, and then from the brute force way we've moved to a more fancier technique, and then we do analysis on that, and then we show that the fancier technique is of course the preferred way of doing things. Now in the case of algorithms, sorting algorithms, we will improve the n-square running complexity. Now the theme of today's lecture is the brute force way of sorting, so I'll just discuss the brute force way, and then you will have to wait until the next lecture to hear about fancier ways of doing the sorting algorithms. Now the very naive way of doing brute force searching is indeed what they would call the bubble sorting algorithm. Now I'm not going to give any source code of bubble sorting. I've just read somewhere on the internet that there are indeed discussions about bubble sorting and whether that should be taught in the first year's curriculum of computer science. Since I'm in Insertion short, that's the algorithm that I will discuss right after bubble sort. It's also in a sense a brute force algorithm. It's slightly different, and even insertion sort is doing slightly better on average and complexity than the bubble sort algorithm. But the bubble sort algorithm is so naive and so easy that I should at least show you how it's working. Now for demonstrating the sorting algorithms today, I have here a pack of cards, and I've already removed some of these cards over there, and so what I'll do is I'll shuffle the cards and then I will sort them using the different techniques. I'm not going to complicate the game by having all sort of different colors for the cards. So what I have here, if you look at the cards, I just have the green at the moment, and then I have the cards that I've picked from. So I have not all the cards. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 cards, and now you should just get used to the cards that I'm playing with. They follow a slightly different rule. The order that we're going to sort them is 7, 8, 9. That should be clear to you. And then this D for Dame, and then König, and then I have 10, Ace, and then I have a Bube. So that's sort of the order of this game of cards that I'm using. For those of you who are not familiar with this card, well, they are actually from a German game called Skat, and they use this nice kind of order of cards. Of course, that's only the Germans that will reinvent the way we usually think of the order of cards. Well, other countries probably also do this. If you have time, play this game. It's really fun. I can also do it not in class, but maybe at some other point. So what I should do is I want to demonstrate bubble sort. So what I'll do is I'll just shuffle this card, and now I'm a bit embarrassed to shuffle this over a television. Since maybe I'm not doing correct. There, good. The camera is not really showing what I'm doing, since maybe I'm not doing it completely right. So I shuffle the cards. If your mother is asking you what you're doing now today, you can say, I've watched my lecturer playing cards. So I put the cards over there, and so we want to sort this card using the bubble searching algorithm. Now what the bubble searching algorithm does is it starts at this point and it moves through this thing, and it compares always these two adjacent elements with one another, and then they will exchange them if the one is bigger than the other. So let's just do this. So I compare 9 with 10. Of course 10 is greater than 9, so I swap them around. Then I compare 10 with this one, and yes, the D is smaller than 10. You should know the rules now at this point, so I swap them around. And then I compare the D with the king, and they are also greater. The D with the 7, I move it down. The 10 with the ace, I move it to this point. The 10 with the 8, move it around, and then of course the 10 with the Buben, and this is smaller than this one, so it will stay over there. Then I do it again. 9 with the D, no. While the D with the king, they are fine. Then I compare these two. Well, I should swap these two around. So this one is bigger. This is fine. since this is smaller than this one, but this one is smaller than this one, so I should move this one to that one over there. This one is definitely larger than this one, so I move it over there, and so there it is. Then I do it again. So this is fine, but I can move this one to that one. They are fine. They are not fine, since the 8 should go there. I compare these two, so you can see this really takes a while to solve this. This king and this 10 is fine, it's in the right place. And then the 10 and the ace, and so they are all in the right order. Then I do it again. Well, this I should put there, and then this should go there, and this is now in the right order, and this is still fine. And I compare these two, I compare these two, and then the rest looks fine to me. I cannot make any changes there, and and then I go through it and I can see I cannot really change this, so it's in the right order. 7, 8, 9, D, Dame, König, 10, Ace, and then the Bube. So, and I've sorted this. So what's the idea of the binary search algorithm? Well, I literally go through this multiple times until and then I exchange the two elements next to one another. And then when I do this, I do the sorting. So I can already start thinking of the running time of this algorithm. So in the very best case, of course, this thing is sorted. Then I just go through the algorithm once and I see it's fine. So in the best case, well, then it's just n. Now in the worst case, well, then I have to do this n times n times. So remember, I have to exchange it, so make this thing completely unsorted. Then I have to redo, so this thing has to bubble all the way down to there if I have to sort it now in the reverse order. So in the worst case scenario, it's n squared, and even if I do it on average, I would expect that it would also be n squared time. I'm not going to give any justification for the average case, but you could do that if you want. I will do a more detailed analysis of insertion sort to show what the average time complexity of that should be. So this is then in a sense bubble sort. You can already see that it takes me quite a while to sort this with this little bit of cards by doing just these exchanges that I've been doing over there. I urge you to go and implement this yourself. It's really easy. It's really just a 4 with a 4, going through it and then exchange all the elements until you don't get any more exchanges, and then you stop. This concludes my discussion of bubble sort, and then I move on to a more another brute force algorithm that we call insertion sort. Now insertion sort, I think the best is again to do this by using my pack of cards. So now I just have to shuffle the cards again so that I'm not completely have the same cards in the same force. So I have my cards shuffled, and then I have the cards over there, and okay, now with the insertion sort we also start on this thing, and we start with the first element. Now I'll just do it again by showing how it's working. And then I said, if I have a list of only this one element, well, is it in its right place? Well, really you cannot do anything with a 9, it can only be there. So this list of one element is now sorted. Now I add next to it the 10. So now the question is, if I add the 10 to this list, is this list sorted? Well, if I insert 10 in this to this 9 list, well, it is definitely sorted since it's in the right order. Now, of course, nothing is going on at this point. So let's add this one. So if I add the Bube to this list, well, is it sorted? If I add it to this list, here it is, since it's 10 and then this one. But now there things get interesting. If I want to add the king to this list, well, it's not sorted. So I compare this one to this one and exchange them to the left. And then I compare this one to this one. If I add this to the list, well, technically this is greater than this one, so I move it down, so I put it there. And so now I have a sorted list. See, 9, king, 10, boober, they are at least sorted. If I add the ace to this list, well, then this list is right. It is indeed sorted. Now I add the 8. Look what's happened over here. Well, if I add the 8 to the list, it's definitely not supposed to be here. Then it's not sorted, so I should put it there. And then I ask the question, is this 8 still in the right place? Now compare it to this one. So I move it there. Is it at the right place? No, it's not. This one is greater than this one, so I can move it there. Is it the right place? Is this one is greater than the 8, so I move it there. And what you see is, as I insert another item into the list, another card into the list, this point where I am, this is always sorted. So in other words, now I have a partially, well, this is a sorted list. So let's do the 7. If I add 7 to this, insert 7 to this list, well, clearly it should not be there. I compare it to this one. No, it should go there. I compare it to the 10. I put it there. I compare it to the king. Well, it should go there. I compare it to the 8. It should go there. I compare it to the 9. It should go there. I think I have done something wrong there a while ago. The 8, of course, if compared to the 9, should be there. Remember, this is not part of the step. I have done it incorrect in the last time. So it should be like that at this moment. Then let's add this one. I've handled this one now. This is the right place. I add the D, Dame, so I should exchange that. Somehow I think I've just this should then go there, and then it should be there. I think I've sorted somewhere. I've arranged my cards slightly incorrect, since I see the 10 here is now the wrong place, and maybe it's because I confused the order of the cards. But the moral of the story is, if I add a new item to the list, I compare it to each one in the list and move it down until the right point. So it's sort of an insertion sort. I insert an item to a partially sorted list, and then I get the right order. I can probably do the search again, make sure it's 100% right, but I think it's 99% right, so that will suffice for this demonstration. So again, what's insertion sort? Well, it's a brute force solution. I mean, I don't do anything fancy, and I move from left to right through the array. In other words, if you remember, if I look at my cards again, I start on this side and I said move left to right. Remember, this is now an array of cards, and if I take this one and set it in the list, then this one this. So this is the left to right. So I one at a time, and then the rule is exchange the next element with a larger element to its left, one by one. So when I add this one, I will move it left or right when it's greater or not. So if I add this to the list, I will say, well, it should definitely, well, of course, this is now sorted. If I add 7 to the list, it should go there, there, and there. At least I can start a card playing business if my computer science career is not working out. In any case, so what I have over here is then another example where I insert A6 into the list. So here I have a bunch of words, so I want to insert the, and then I look to the one to the left and I see, well, the and you should change around, and then I check it with was, and the and was should change around, and then I realize at this point it's its right place. So this is kind of how this algorithm proceeds. So here I have another table of doing it, showing this example. Now, I mean, what I would actually urge you, if you watch this video now, is that you actually just pause this, and then you look at this table and make sure that you can actually get to this table again as well, by applying the searching algorithm, this idea of how not searching, of how I sorted these cards. Do this for this table, and then see if you can get to the same table. What I should highlight at this point is, of course, that This black things are the things that changed. That's instructions that takes place, and then this head is the current item that I move. So let's just do this together. Maybe the first 2 rows. So I have this is the list I start with. Then I compare head with was, and I move it there. Then this is a partially sorted list. I'm happy. Then I add him to the list. Well, if I compare him with was, then it should go there, and then had and him is fine, so the list stays the same. Then I add and to the list. Well, if I add and to the list, it will propagate all the way down. Since I compare it pairwise to this one, it will propagate to this point, the start list. I add you to the list, and so forth and so forth. So let us just look then at the implementation of it, of this sorting algorithm. And this is just now the Java code of what I've done here and with the playing cards. So let's go through it line by line. So again, n is the length of the array A that I'm sorting. And then I go with this element through the array. Look there that I start at point number 1. And of course, if I have my cards here again, remember the idea is that the array at the current index is always sorted. But if I start with this one thing, I mean there's nothing I can always do to this one. This will always be trivially sorted. So I start with the 1 after, so at element 0, 1. So that's why I start at element 1 there. And so while I is less than n, so in this case back to my cards until this point, I go through it one by one. Then I have the second loop. And the second loop starts at the current position I'm adding the new at I. So back to my cards. If I is this point, then I move from this point backwards. If I is 2, then the second loop will start at this point 2, since I'm inserting 2 in the list. Sorry. So there I have the second loop starting at the point where I insert stuff, and I move the elements to the end where it's needed. So I compare the element j to the previous one, and if it's greater, then I exchange it. Well, actually smaller, so depending on what this compared to is returning. In the case of the cards, if I didn't use the compare to, I would just use the naive. I would replace that function with is this card greater than the other in playing order. So back there, I exchange them, and otherwise, if I don't do an exchange, it means that this sub-array that I've created, this sub-list, when I inserted it, that one is sorted. So when I move this one, well, I don't exchange it with this one, I don't exchange it with this one, this. So there's, if I don't exchange it to the one to the left, it means that I will not do any more exchanges, since this sub-array is already sorted. So I can just break. And exchange, I mean that you've done in the first week of your classes, so I'm not going to discuss this. First week of first semester. Okay, so this is the running time. This is the implementation of insertion sort. So what's the game with all these things? Well, the game with new algorithm, you know it now at this point. I'm having an algorithm and I should do analysis on the algorithm. So that's what we're going to do now. I have the algorithm and I'm going to do analysis. So here I have just a plot of a graph of the running time, the number of comparisons, millions, and the input size. And now you will see that if the let's do the easier one, the ascending case. So that is, in other words, the elements are already sorted. Now in this case, if you look at this loop, I mean basically this loop will run once and you will just check the previous one. You see, it's like an if statement, this loop. Then I cannot really exchange it, so I break. And then I go to the next one, the elements. You basically go through the list and check that it is sorted. And so you would expect the running time to be of order n, and that is what you see over there. And then for the other two cases, that is for the random case and for the descending case, we have different running times. Now I should pause for a moment here. Well, I'm not going to pause the video, but I'm going to pause what I'm doing there and say what's going on here. I've been mentioned this actually in the previous lecture as well a couple of times, and now as well, that I have this descending case, the random case. And so what is this all about? Well, it depends the number of comparisons that I make. So in other words, the number of actions that I take in the program depends on the input data. May I remind you that our goal is that we count the number of times instructions take place. And then the number of times, the frequency, is the running time, the estimate of our algorithm. So in other words, if n squared actions takes place, then the running time is of order n squared. So that is what we're trying to do. Now with the algorithm that I have over there, for example, it's not so trivially to just count it by saying this loop is running through n and this one starts at I and goes to 0, and boom, I know the number of exchanges take place, since there's this break statement sitting there. And I mean, so you don't know when this will break. It depends clearly on what the data is looking like. I mean, if the data is completely sorted, as I've said it before, then it will break always at the first element. However, in the worst case, it could be that the data is completely unsorted. Then it will go through all the things and it will not break. Then it will actually get to this point where it's 0, j is 0. So that's why we have now these different kind of cases. We have the case where it's the best case scenario, so the data is sorted, and that's usually easy to analyze. Then we have the worst case scenario, that is where we know that's descending data. And then we have sort of a random, an average case, where you sort of have to guess what's happening to the data. Since you have this data now and you don't know what the input data is looking like, so you have to make some assumption of how would you think the data would, what's typical case of the data. If you do kind of analysis, the best is probably to make some random data and then see how my algorithm is behaving on the kind of random data I get, and then have an estimate for that, since that's ultimately how your thing will work. If you have always ascending order, then there's no need for this algorithm to work, since then the data is sorted. If it's always descending and you know that, well, then I can also solve this problem quite easy, since then I just get the data in the reverse order and I have my answer. So it is actually this vague case of where the data is just random, the cards I've just shuffled, so they're in a random order, that we're interested in. So let's look at the analysis again. So here I have the worst case. So in the worst case, I would require for iteration I comparisons. Remember, with iteration I mean, so I'm inserting this A's, for example, now into this list. So if I, in the very worst case, so let's make this the very worst case, if I insert 7 into this list, so that is item 0, 1, 2, 3, then I would have to compare it to this one, 1, 2, 3. So that's the very, very worst case that I have, that it has to move to the beginning of the array, of the list. And that's why I have then this iteration I requires I comparison. So in total for iteration I, 0, I have 0 iterations. For iteration 1, I have 1 iteration. For iteration 2, I have 2 operations, and until n minus 1. And of course, you should know this now, that the sum of 0 to n minus 1 is approximately equal to n squared over 2. So in the worst case, we have a running time complexity of n squared over 2. Now let's look at an average case, a random case, where I've shuffled the cards. So here I would argue then that iteration I would take on average I over 2 comparisons. So I'm not sure how I can really demonstrate an average case, but let's maybe put let's make it like this at the moment. So this is perhaps where I am at the moment, and let's say I want to add 8 to this list. So what I'm arguing is that for the sort of the random case, the average case, I would move, if I insert this one into the list, I would move it approximately halfway in this list. Of course, sometimes I might insert this one and then I would not have to move it halfway. Somewhere I would have to do it all the way, sometimes just one element at a time or something like that. But the point is I move it sort of halfway into this list. And so I have then this, that I have the total number of operations is the 0 plus 1 plus 2 plus divided by 2. That's halfway. But of course, you know that this sum is approximately as tilde n squared over 2. That not approximately, that is the case. Well, there are some lower order terms as well. And then I divide by 2, so it's just over 2, so it's n squared over 4. But the moral of the story is that this algorithm, in its worst case, and its average case, are both of order n squared. Whether that's now over 2 or 4, that doesn't really make a difference. If I have a very, very, very big number and I divide it by 2 or I divide it by 4, I will still have a very big number. So let's get back to my my favorite example. So a credit card company sorts 10 million customer account numbers for use with binaries. Well, this is perhaps the wrong slide there. It should not have been there. That's the sorting one. But in any case, if you can think now of an example where this credit card company wants to sort it by do searching, then it will definitely also not run on their toaster if they're trying to do that. But here is a better way of looking at things. If I can do on a laptop, say 10 to the 7 comparisons, and on a supercomputer I can do maybe 10 to the 12 comparisons per second. Now I do this insertion sort. Remember, it's about the number of comparisons that I'm counting. Since remember, this is, if we do analysis of running time, we're interested in this inner loop, and in this inner loop we're doing comparisons. So we're counting that. Now suppose I can do this kind of comparisons on my laptop and on a supercomputer. Then for 1,000, if I do insertion sort, well, it's almost instantly I will do that, so it will not be a problem. 1 million, well, on a laptop it will take a day, and on Google's computer or the supercomputer, a second. If I do 1 billion, and 1 billion is not really a big number for sorting, we can use big things, then it will take 3 centuries on a laptop, and on a supercomputer 2 weeks. That's still a very, very long time to do that. So now, of course, at this point you can argue and say, well, that's fine, let's just wait for a new computer a bit longer, and when a new computer comes, then I just buy that. Maybe Google's supercomputer, you could argue that I want to sort 1 million entries. Well, I don't want to wait a day, so let me just wait until this supercomputer of today is becoming the laptop of tomorrow, and then I can do it in 1 second. But there's a twist in this story, or another part of it, and that has to do with Moore's law. Now in 1965 there was this person, Gordon Moore, and he was the co-founder of Intel, and he wrote the following: the complexity for minimum component cost has increased at the rate of roughly a factor of 2 a year. Certainly over the short time this rate can be expected to continue, if not increase. Over the long time the rate of increase is a bit more uncertain, although there is no reason to believe it will not remain nearly constant for at least 10 years. So there is then this, that was sort of the starting point of this Moore's law, and Moore's law can basically stated as the transistor density on a chip doubles every second year. So in other words, we sort of get double the speed, you can sort of argument it that way, every second year. So we doubles the density on the chip every second year, and so you can specify this in terms of memory, of disk space, so you can have always faster memory, always faster disk space, always faster bandwidth, computing power will, computers will be cheaper. In fact, there is this plot over there of, it's now a bit difficult to see over there, of the components that you can get for a price of $1,000 on this side, and then the year, and this is a log plot, and you can see that we have this exponential kind of behavior sitting there, since we have a straight line in the log space. Just to give you another idea of what's going on there, is the amount of transistors produced now each year outnumbers the world and population by 10 to 100 times. So we have 10 to 100 more transistors in this world than we have ants. Now you could use this now and argue that, well, so just wait and then the faster computer will come. But now let's look at this argument over here. So we have a quadratic algorithm, and so we could argue, well, we have now a new computer that will be 10 times faster. But the problem with the human race, if we have a 10 times faster computer, we will also have a 10 times as much memory, and so we will have a problem that will be 10 times bigger, since that's what we're trying to do. We could have stored 1,000 pictures, and now we have a hard drive that can store more place, so now we store 1,000 pictures. So we just, when we have more things, we do more. So the problem is, if we make this problem 10 times bigger, and we have a 10 times faster computer, then the quadratic algorithm will take 10 times longer, even though we have a new computer. So that's why this Jaron Lanier said, software inefficiency can always outpace Moore's law. Moore's law isn't a match for bad coding. So what's the moral of the story? Well, the moral of the story is we need a linear or a linear rhythmic algorithm to keep pace with Moore's law. A quadratic algorithm will definitely not work for to keep up with Moore's law. And this is the point where I want to stop. So what I've done in this lecture is I've given an overview of two algorithms, the one being bubble sort, and then the other one in a bit more detail of insertion sort. I've shown you how they worked, and then we've done runtime analysis of that. And the runtime analysis then said that the running time is of order n squared, so it's a quadratic algorithm. And then at the end I've made a case, it's almost like I'm in court, I've made a case now in saying that a quadratic algorithm is surely not enough to solve this problem. We cannot wait for a faster computer if we want to solve bigger problems, if we want to sort bigger problems. And so we have now this point that we need a faster algorithm. Of course, I know that there is a faster algorithm, that's why I'm presenting this case. Sometimes you just don't get something that's faster than quadratic, and then you have to live with it. But if you wait until the next lecture, I will then present a linear rhythmic time algorithm for sorting, and this would allow us to actually solve this much bigger problems that we want to do. So until the next one, next video lecture, until the next lecture when I see you again, goodbye.